Hello everyone, I'm Bella and I'm here with my lab mate Adarsh, and we're both PhD students in Bliss Lab. So if you went on the lab tour yesterday, you might have ran into our home. But we're here today to talk about some work that we've been doing on joint communications and sensing, specifically using an OFDM waveform. So I should have buttons right here. So here's a quick overview of the topics we're going to talk about today. But as it's been alluded to, this is kind of a hot topic at the moment, but as the number of wireless communication devices continues to grow, and then with that, the radar and sensing application space also continues to grow, there is an arising problem of spectral congestion. And with that, there's a need for smart spectrum management solutions. And one solution that potential solution that people are exploring right now is joint sensing and communications. So using the same frequency band for both radar and comms application, be that switching off or both simultaneously. So the goal of our project and what we're here to talk about today is specifically an SDR-enabled joint sensing and communications platform that we've been working on building, and the results that we have for you today are using an OFDM waveform. So the radar application that we are exploring in this work is specifically human vital sign monitoring. So if any of you were at GRCon last year, I presented on some work using a continuous wave radar built with a software-defined radio that we use to measure heart and respiratory rate. So this is kind of an extension of that work, and there's a lot of very interesting research going on in that space using a small-scale radar system, but not a ton using software-defined radios. So we've had some fun doing that. So a radar or a joint sensing and communications system can be operated in 3 different configurations. So one of those would be a monostatic configuration where you're not using your comms link, but you're just from one single unit transmitting and then doing your radar processing on that specific unit. The total alternative to that would be a bistatic mode where you are transmitting from one unit and then receiving at another unit and doing both your comms and radar processing on that other unit. But the mode that we are working with today is a mixed mode. So we transmit from one unit and then we do our radar processing on that unit, and we do our comms processing on a second unit. All right, so now I'm going to pass it over to Adarsh to keep going.
Thank you. So as Bella was saying, so the interest in using OFDM waveform as opposed to any other comms waveform is just because it's popular, I guess. So if you could somehow utilize it for dual link, that would be nice. So just a refresher course, I guess, on what OFDM is. Basically, you have a certain bandwidth that you end up fragmenting into orthogonal subcarriers, and each of the subcarriers would have a bunch of payload inside it that you end up decoding. We all know that, or many of us know that there are a lot of advantages to the OFDM waveform in sense. It's robust to multipath, better spectral usage, and robust to jamming and interference. Of course, there are some demerits with the PA-PR of the signal, but I think we can still utilize that in our favor. So now that we know that, so just another crash course on the OFDM radar. Basically, the OFDM radar operates in a very simple mechanism. That is, you have a transmitter and you have a receiver. The transmitter transmits something, the receiver observes that. And if you just divide one symbol by the other, you end up pretty much canceling out anything that's in the symbol, and then you're left over with some channel component, any Doppler, if it's observed, and the delay of the target, which can be used for ranging purpose. It would be important to note that in this formulation, the delay over there is constant, so it doesn't move, but for our problem, the delay is slightly time varying, so we'll talk about that more in the future. In terms of the selling points of the OFDM radar, pretty much the OFDM radar has low operational costs because you can integrate it with existing systems. So so there is that to it. And this is where we come to the GNU radio system design. Pretty much the system design is kind of off the shelf of whatever is there in the GNU radio tutorials. You end up having a comms link, which has both timing and frequency corrections to it, and then the radar / comms transmitter. Over there, we just put a custom payload and then expect it to observe something. So setting this up would probably take a day or two, and it wouldn't be too hard. So now moving on to, I guess, what vital signs are and why is there a lot of buzz in this. Basically, vital signs are motions induced by your body. And two of them which we are interested deeply in are the breathing rate and the heart rate. So every time your chest moves back and forth, as shown in the dummy, it induces some motion, hence a Doppler. The heart rate, though, is more about the pulsation of the heart, so it's not easily visible, but it is possible to deduce that if the radar can penetrate enough. Or it induces motions on the surface. So with that being said, I guess there are some technicalities to using the OFDM itself. So the induced Doppler is pretty much the same for us across the entire spectrum because the motion is so slow that it doesn't really cause too much smearing. We put the subject at close range, so and make sure that they're fairly stationary. And then there's a catch about the subcarrier spacing has to be about 1 order magnitude greater. So in our case, the largest heartbeat possible is it's about 190 beats per minute for the infant, and that translates to about 1 kilohertz in subcarrier spacing. So you can pretty much get away with doing this in very low bandwidth. Oh, okay. So for the experimental setup, it is a small budget setup. We have two B210s. One acts as a, we dub it as monostatic radar, though the antennas are placed about 1 meter away. But they're on the same unit. So we call that as monostatic. And then there's a comms receiver away from here on the other side, which can receive whatever signal is being transmitted from here and decodes it. In terms of the setup itself, it's a fairly long payload sequence, so that it acts more like a pulsed radar. We didn't go too much into the effort of actually trying to put in an industry standard OFDM payload and preambles because the aim of the project was to prove that it's possible more than optimizing the bounds of this. So with that being said, the bandwidth that we operate on is like 1 megahertz or so, and then at this bandwidth, the range resolution is so poor, right? It's 150 meters for every bin that you consider. So, and in close range, that makes a real big deal because you don't really know. You will have a time varying delay that you need to kind of compensate. Yeah. With that said, I guess we'll just go to the comms waveform. Again, we didn't focus too much on the comms link because it's done and we could optimize it further. The comms link is just the standard comms link. There's nothing much we did to it. It has just one sync and a long payload, so we expect the decoding to be bad. There were no, it was not, it had no FEC in it, so it was bad. But it does, after equalization, you can see that there is some amount of change. So with that said, now the actual fun part of the project, I guess, is that how could you use this OFDM to actually detect this, right? So I think it should play, right? Yeah. So what you see is the observed received waveform at the receiver. it was transmitting, I think, at minus 5 dBm with a gain of on the RX of 50 dB, so fairly low. And then every time that the heart beats and moves, sorry, every time Bella, the subject, moved her chest back and forth, you can see that there's a change in the amplitude, which makes sense. And hence, we can kind of, at least looking at just the waveform, you can say that, okay, there's something interesting happening over there. So with that said, we'll walk through the processing chain that we use for the vital sign recovery. As mentioned earlier, the OFDM radar division has to first take place, so you get some time-varying channel residue. We do some clutter mitigation to remove some background noise that is there. And after that, we do some coarse channel equalization so that the noise is further reduced. The next block is, I call it DC offset, but it's more about the time-varying range offset correction that you do. And after that, the Doppler FFT and an averaging filter so that the noise is reduced. Typically, because we are kind of trying to estimate the beats of the heart in like sub-hertz category, like below 1 hertz. So the phase noise of the the phase noise of the radio itself comes into a lot of play, and hence there has to be some way to mitigate that. So I guess these are some of the preliminary results. So on the plot, when you look at the left, the first plot on the top is the amplitude plot of what we just saw. So if I take a running max of whatever signal peak that I get, I can observe that there is some pattern of change in the amplitude itself. That's not too interesting because you can't really deduce anything out of it. However, when you look at the phase plot, you can see that there is some change in the phase, but we don't entirely know what's going on there because there is a time-varying range because it's 150 meters across, and then you don't really know what's happening in between. So you do have to remove that in some sense. So you end up doing something simple, such as a DC offset correction, which would kind of reduce the entire, or normalize the whole value down to what you expect to see. So so the last plot over there that you see is pretty much after the correction. And once you correct that and take the FFT, you can see that there are 3 distinct peaks. We don't know what the first peak is. It could be probably the fan or something, or something slower than that, like a paper moving or something. But the 2 other peaks that are interesting for us is the actual breathing rate and the heart rate, which you can see. Bella took roughly about 22 breaths for that minute. It was pretty hard breathing. But it did identify that, and then the heart rate itself was about 63 beats per minute, so that went good. In terms of the results itself, we didn't actually simultaneously measure it using a PPG sensor or an ECG sensor, because I guess one, it was a small project, so and 2 is that validation would probably require more time. Yeah, so I guess that's the whole thing. So in terms of the project we did and all of that, I guess we operated the OFDM on the lowest bandwidth possible, and then we could still see something. The reason we did that was for multiple reasons. One was because initially we tried to operate these on these small nooks, and we needed like at least a long sequence so that we can get good spectral estimate, and we couldn't process that much on the nooks. So we tried to reduce the bandwidth, but that caused other issues. So eventually we processed it on MATLAB. So yeah, so I guess in terms of the how do you call it? The resulting importance of this work is that we could use it in the lowest bandwidth possible. Some future work that we could do is that right now we use just known sequences just as a pulse radar. We could always expect some random comms user to decode the data and then see, which would cause more errors, but it's possible. We could also improve subhertz estimation accuracy and use real time for GNU radio. Yeah, so I guess that's project.
All right, very, very cool. Do you have any questions? Do?
On the previous slide, I'd be curious to see what that graph on the right looks like without the subject sitting there.
Yeah, we don't have that over here, but ideally you would, I'm guessing you would only ideally, I guess you would only expect the first peak to exist, because we don't really know what it is. It's like 5 beats per minute or something, and I'm not sure what oscillates at 5 beats per minute. Maybe like a paper or something. I don't know what it is.
So you have this. You might have the same thing, but then that without the 2 peaks.
Yeah.
Okay. So what was the bandwidth actually? I know you said it was low, but then I forgot the.
It's 1 megahertz.
Oh, okay.
Yeah.
Interesting. Okay. Any more questions? So I'm still a little bit excited to see my own thesis cited in your slides. All right. Thank you very much.